Determine if the series converges or diverges. We have negative 4/5 plus 8/6 minus 12/7 plus 16/8, and so on. Notice we have an alternating series. Let's begin by writing sigma notation for the infinite series. And now to analyze the numerator and denominator separately. Notice in the numerators increase by 4. 4 plus 4 is 8. 8 plus 4 is 12. 12 plus 4 is 16, and so on. And the denominators increase by 1 each time. 5 plus 1 is 6. 6 plus 1 is 7. 7 plus 1 is 8, and so on. So we could use the formula for an arithmetic sequence for the numerator and denominator, which we did in previous examples, which again is the formula a sub n equals a sub 1 plus the quantity n minus 1 times the common difference d. But for this example, we might be able just to use pattern recognition. If we let the index be from n equals 1 to infinity, notice 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12, and so on. We can express a numerator as 4n. And for the denominator, 4, we can use the formula 4 plus n. Notice 4 plus 1 is 5, 4 plus 2 is 6, 4 plus 3 is 7, and so on. And now we need to deal with the alternating sign, which means we'll have a factor of negative 1 in the numerator, and let's try the exponent of n. Notice when n is 1, we do have negative 4/5. When n is 2, we do have positive 8/6, and so on. This is the correct formula to generate the terms of the series. And now because we have an alternating series, we'll apply the alternating series test, which is shown here on the right. To apply the alternating series test, we first determine a sub n, which is a non-alternating part of the formula. The series converges if two conditions are met. Number 1, the limit as n approaches infinity of a sub n equals 0, and 2, a sub n plus 1 is less than or equal to a sub n, meaning the terms of the non-alternating series would be decreasing. To begin, notice a sub n in this case is 4n divided by the quantity 4 plus n. So for the first step, we'll determine the limit as n approaches infinity of a sub n, which is 4n divided by the quantity 4 plus n. The shortcut to determining this limit is to recognize the degree of the numerator and denominator are the same. They're both degree 1, and therefore the limit equals the ratio of the leading coefficients, which would be 4 divided by 1, or 4. Or we could apply L'Hopital's rule, which states this limit equals the limit as n approaches infinity of the derivative of the numerator with respect to n divided by the derivative of the denominator with respect to n. Well, the derivative of 4n with respect to n is 4. The derivative of 4 plus n with respect to n is 1, giving us the same limit. The important thing to recognize here is this doesn't equal 0. And therefore we can go ahead and stop. This limit indicates the non-alternating series would diverge by the nth term divergence test. And if the non-alternating series fails the nth term divergence test, so does the alternating series, and therefore the given series diverges. If we want to be more formal, we could apply the nth term divergence test to the formula for the alternating series, which may seem more challenging because of the negative 1 to the power of n. But if the limit of the non-alternating formula is equal to 4, then the limit of the non-alternating formula will oscillate between positive 4 and negative 4, which indicates the limit doesn't exist, and once again fails the nth term divergence test. So the given series diverges by the nth term divergence test.